Want to welcome you to my lecture today. Today, I'm actually going to be walking you through another interesting topic in statistics. I told you the other time that statistics is like a story that goes on and on and on. Okay, so today the focus is actually going to be on Poisson regression model. Well, let me tell you this. I think I would like to have a recap. Okay. I'm going to have a recap. I actually want to go with, retrospective. I quickly want to revisit what we have done before so that you'll be able to see the difference between what we want to do now and what we've done before. Now, let me first tell you this. We find ourselves in a world where we always want to investigate if a relationship exists among variables. I'm going to say that again. We find ourselves in a world where we always want to investigate whether a relationship exists among variables. So because of that, we're actually going to use regression. But the question now is, we're going to use regression model. The question now is, what type of regression model are we going to use? Because we have different kind of regression models. Now, I could remember I started from linear regression model. We actually fit a linear regression model in a situation where we want to characterize relationship between variables, and we have an assumption that the relationship is a straight line. I'm going to say that again. We want to actually characterize relationship between variables with an assumption that the relationship between the response and the predictor is that of a straight line. And not only that, another requirement for fitting linear regression, apart from the linearity, normality, and so on like that, the nature of the response variable has to be continuous. I'm going to say that again. Another reason why we fit linear regression, okay, to characterize relationship, between variables, in addition to assumptions, of linearity, normality, independence, and so on like that, the nature of the response variable has to be continuous. Now, in a situation where the nature of the response variable is not continuous, but the nature of the response variable is categorical, of course, we can no longer fit linear regression. And I walk you through what you can fit, which we call logistic regression. So we fit logistic regression in a situation where the nature of the response variable is categorical. Now, I'll also walk you through what I call, the variance of logistic regression model. I remember the other time I actually walk you through what I call the analysis of categorical variable, the multinomial logistic regression, and the ordinal logistic regression, and the beta regression model. Now, let me tell you this. As we have the variance of COVID, we also have the variance of logistic regression. Now, when the response variable is categorical and the levels of the response variable is ordered, what do I mean by ordered? Situation where the difference between the levels are not equal, I remember I give you an example that has to do with, gold, silver, and bronze. Okay. Then in that situation, we're actually going to use ordinal logistic regression. But in a situation where the numbers of the levels is more than 2 and they are not ordered, then we use multinomial logistic regression. And I also walk you through situation where the nature of the response variable is categorical, and then the predictor is also categorical. Then you're going to use analysis of categorical variable where you make use of the chi-square test, where you actually want to test if there's an association between the levels of predictor and the levels of the response. I remember I walk you through when we're trying to see whether there's a connection between the age at first pregnancy and the rates of getting cervical cancer. Now you can now see statistics is like a story, and the reason why it is a story is because we needed to be able to identify the appropriate regression method that can actually be used to characterize relationship between variables. And what is very, very important is the nature of the response variable. Now back to Poisson regression model. Situation where the response variable is not continuous, is not is not categorical, it is not a rate or proportion, because if it is a rate or proportion, we use beta regression model. Okay, now, but it is a count. What do I mean by count data? You know, when you talk about count data, you're talking about discrete variable where you can actually, you can express that number as a whole number, like the numbers of goals scored in a match, like the number of students in a class right now is a count data, like the number of patients in a particular hospital, that's a count data. Okay, like the number of award won by student, that's a count data. Okay, you cannot have it to be 7.5 or 9, but you're going to have it as a whole number. Now, situation where the response variable is count, then we're going to use Poisson regression model. Okay, and today I'm actually going to walk you through this modeling counts, contingency tables, Poisson regression models. We're actually going to have part 1 today. On Monday, we're going to have part 2. And I want to tell you, this topic is actually going to be the last topic of this semester. Okay, only that we're going to do this next week as well. Okay, now, modeling counts. Why count data? I think we need to first identify what are the examples of count data. When I say count, number 1, it could be the number of traffic accidents per day. Accidents don't just happen, okay? But accidents do happen, okay? So how can we actually model that? Because we know that there are some predictors, there are some factors that could lead to that. And what we actually want to do in Poisson regression is to be able to isolate the effects of predictors to the occurrence of the response. Okay, so when you talk about the number of traffic accidents per day, you talk about the mortality count in a given neighborhood per week, or you talk about the number of coughs in a concert hall per minute. People don't just cough. You got what I mean, right? Or you got to talk about the numbers of customers arriving in the shop daily. We have other examples, like for instance, you go to a grocery store and you saw a lot of people ahead of you. Okay, you go to a grocery store now and you saw a lot of people ahead of you. Of course, you may want to know what is responsible for that. What is responsible for that may be Maybe the restaurants actually offer some products on discounted price because according to the theory of consumer behavior, consumer will like to buy more things at lower price. And when they hear that the price of a particular product is being discounted, they will want to go. Okay, that is number one reason. Number two reason may be that, okay, maybe during the festive period, look at what happened in Black Friday. Okay, what happened in Black Friday don't happen in an ordinary day. Because in a Black Friday, consumers will actually go to the restaurants in mass because they know that the customer are they actually going to get discount. Okay, another example I'm going to cite that from politics. You know, when we're talking about count data here, we're talking about something that occur in an interval, and it's a very, very rare rare event. It's something that occurs in a blue moon. It's not something that just occurs regularly. In the last election in the United States, you know, there was some set of politicians that believe there was electoral malpractices. But let me tell you this, that is very, very rare. You know why it is very rare? Because if you want to look at the integrity of the United States in the world in conducting election, they have integrity. But let me tell you this, the fact that an event is a real event, that doesn't mean it cannot occur. I'm going to say that again. The fact that we call an event a very rare one, that doesn't mean it cannot occur. How do we model that? How do we model the probability that the election will be rigged in the United States? That's why the fact that the United States has a very high electoral integrity in the world. Okay, you want to talk about the number of snake bites in a year. Snake don't just bite, okay? Or you want to talk about the incidence rate of disease, okay? Those are candidate. And particularly those of you that love sports, we can actually model the numbers of goals that will be scored by a soccer team. If I don't know whether some of you are familiar with the championship in the United States, or you are familiar with English Premiership in the UK, where you talk about Manchester United, Arsenal, and the like. We know they play a form of a league, home and away matches, and at the end of the day, a team that has the maximum point will win the league. You know, we can actually use Poisson regression model to predict the numbers of goals that a team will actually score at the end of the season. And what do you think will be the predictors? The predictors will actually going to be the goal average, number one. And another predictor could be the home advantage, because they play on home and away basis. And of course, some team play very well when they are playing at home because they have their fans around that will be, cheering them. Then what about the offensive power of that team and the defensive power of the opposing team? Those are the variables we put into consideration to have a prediction, to predict the eventual winner. Poisson regression can be used. Okay. Now, we have a lot of examples. I said, even in public health, count data are particularly important in measuring disease rate. And we often count the number of people acquiring a particular disease in a given year. Right now, there's now Omicron variant of the, COVID in the US. I think the first one was detected in California, state of California. I think I had the news yesterday that another one was detected in the state of Minnesota. So we may, what the countries in the world are doing now is to try to know the number of people that have that disease, that have that version of disease. The number of them can be counted. It can be modeled. That's a count data. So if we want to model relationship between some factors and the kind that are, of course, we're actually going to use Poisson regression model. Okay, so I think I've mentioned disease rate, and I said Poisson regression will allow us to measure association between incidence and risk factors of interest, adjusting for other related covariates. So that is what Poisson regression does. Okay, when you have identified predictors, we can actually look at the effect of the predictors on the count data. I told you the nature of the response variable here is actually count. Okay, and let me also tell you this. We also use Poisson regression to model contingency table. You know what we did under the analysis of categorical variable, Poisson regression can also be used. I'm going to say that again. You remember the other time I walked you through the analysis of a categorical variable, right? Where we have a contingency table, right? Where we have two categorical variable cross tabulated. Okay, we use a chi-square, right? We can also use Poisson regression model to do that. So Poisson regression can also be used to analyze contingency table, because the contingency table has counts. Okay, when you look at the contingency table, it has count data, and that is the reason why Poisson regression can also be used. Okay, the next, if you take a look at this, of course, we have a whole new model now with counts. The models that I've discussed with you before, I've walked you through linear regression model, and I've walked you through logistic regression model. For the linear regression model, there is an assumption of normality or of errors. Okay, the error follow normal distribution, but in logistic regression, it is binomial. You know that, right? Because the nature of the response in logistic regression is categorical. Okay, so which means the count data that we are talking about, okay, do not follow any of those distributions. I'm going to say that again. Count data do not follow normal distribution, do not also follow binomial, because it's a count, okay? And you know what? It's a count, and typically it is actually going to be skewed, and particularly it's going to be right skewed. You know what I mean by skewness, right? The skewness is a measure of departure of data set from normality. Okay, we have a way to investigate skewness. Of course, with the normal KQ plot or with the histogram, you're actually going to see whether the distribution of the data set is skewed to the right or skewed to the left. The moment the data set is not skewed to the right or skewed to the left, then it means it is symmetrical. It means it is evenly distributed, which means it's going to have a double bear shape, and which means it's normally distributed. But for count data, they are not normally distributed. Okay, and if the count data is not normally distributed, then we are not going to use a model in statistics that rely under the assumptions of normality. Okay, then we need to know the probability distribution of the response variable. At times it looks as if our models are failing us. Our models are not failing us. I could remember what George Box said. George Box said, and I quote, "All models are wrong, but some are useful." I'm going to say that again. According to George Box, all models are wrong, but some are useful. Now, some that are useful is because we are following assumptions. If we're not following assumptions, of course, there is going to be a problem, because every model has assumption, and we got to make sure the assumptions are met before we can actually use a model. Okay, now what I'm trying to tell you now, we need to know the probability distribution of the response variable, okay, in order for us to move ahead. Now, you remember before we've talked about the expected values. Of course, we talk about the expected value when we're working with the linear regression, where we're going to say, okay, what is the expected value of the response given that the predictor equal to something? That is an expectation. We do that in linear regression. If I spend $5,000 on advertising, how much am I expecting the volume of sales to be if I'm looking at the effect of a month spent on advertising on the volume of sales? That's an expectation. But with the logistic regression, we talk about log odd, right? You remember log odd ratio. That's what we talk about in logistic regression. Okay, but you know what? When we are modelling count, we don't talk about the expectation that we talk about the linear regression, and we don't talk about log odds. Okay, but what do we talk about? We talk about incidence ratio. Okay, incidence ratio. Okay, then Poisson regression actually provides us with a framework to handle counts data properly. Okay, and that is the reason why we actually want to feed Poisson regression. Okay, now before we go into Poisson regression model, I think we need to understand a probability distribution called Poisson distribution. Because we want to talk about Poisson regression, then we need to be able to understand what do we mean by Poisson distribution. Because the distribution of the counts, data that we're talking about, we said it is no longer normal. Then what is the distribution? Okay, the distribution we are actually assuming for that is Poisson. Then I need to walk you through the property of Poisson distribution. Now, when we talk about, when we have a Poisson distribution is a discrete random, form of a distribution, because in statistics, what do we mean by probability distribution? I think let me just tell you that. I know this is not a probability class, but we live in a probabilistic world, and for us to be able to understand our environment, for us to be able to take a decision that we're not going to regret. I'm going to say that again. Every day we want to take decision, right? We want to take decision on medical. We want to take decision may be in economy, decision may be even in marital, and so on like that across the board. And we live in a probabilistic world. Then how are we actually going to take decision that we're not going to regret? For us to be able to know, for us to be able to take decision we're not going to regret, that we need to be probabilistic inclined. We need to have an average knowledge of probability. What do we mean by probability? The probability is just trying to tell you the number of occurrence, like the frequency of occurrence. It means you have a sample space, okay, and in a sample space, there are possibility. Sample space means possibility, right? There's a variation in this world, and that is why the sample space is going to tell you the collection of possible outcome. Now, the probability is now going to tell you, we need to know what is the frequency of the numbers of time a particular event in the sample space will occur. That is what we mean. And in every data set, we actually need to know what is the probability distribution. Now for Poisson, distribution, probability distribution is discrete. And of course, that's why we're using it to model counts. Now, what we're trying to say is that for Poisson now, the occurrence of a random event in an interval of time are independent. Okay, when you are waiting for customer, then maybe you are dealing with the arrival of customers to a particular maybe restaurant. When you wait between 8 and 9 a.m. for customers to come, at time customer may not even come. Now, what we are trying to say, because the arrival of customer to a restaurant is random. It's customer arrive randomly. You understand what I mean? So what we are now trying to say here, the occurrence of random event in that interval of time are independent. Are independent means it doesn't depend on the time you have waited. That's what I mean. So if you wait between 9 and 10, and you wait between 10 and whatever, so the number you are going to see are independent of each other. That's what we mean. Then the next one is trying to say, and in theory, an infinite number of occurrences of the event are possible. They are possibility of an event that can occur within the interval. But let me tell you this. When the interval is very, very small, probably between 9 a.m. and 9:01, and somebody is trying to say, what is the probability that between 9 and 9:01, 1,000 vehicles will be involved in an accident? That probability will be approximately 0 because the interval of time, you get what I mean? So we have situations like that. So these are the properties, these are the assumptions for the Poisson distribution. Now, what is the formula? I'm going to walk you through the formula now. Right now, we're working on Poisson distribution, not on Poisson regression model, because Poisson distribution is an underlying distribution for the error term in Poisson regression model. And that's why we need to understand what a Poisson distribution means. Now, take a look at the formula I have now. This is a probabilistic expression of a Poisson distribution. What is the meaning of X? X start from 0, 1, 2, that's a count. When X equal to 0, an example is you go to a grocery store and there is no customer ahead of you. Or you could have one customer ahead of you, 2 customers ahead of you, and so on like that. Okay? Now, lambda is what we call the expected number of occurrences in the interval, and at times we call that incidence rate. Lambda is an incidence rate. Okay? And you know what? When you take a look at this distribution now, the parameter in the distribution is lambda, which we call the incidence rate. And let me tell you this. When you're trying to change the values of lambda, it's going to be giving that distribution a different shape. Now I'm going to show you something now. Take a look at this shape. When lambda equal to 5, and I draw the histogram, using that distribution, this is what I have. When lambda is no longer 5, maybe I increase lambda to 30. Oh my God, the distribution is looking like a normal, right? Take a look at that. So which means an important parameter for Poisson distribution is lambda. When I change it, when I decide to vary the lambda value, I'm actually going to have different shape. Take a look at that. Okay, now this is what happened. One distribution leads to another. Why do we have a Poisson distribution? Poisson distribution actually comes from binomial distribution. And let me tell you this. What do we mean by binomial? Binomial distribution is when the nature, we use it to model a variable that have 2 possible outcomes. That's how we use that in logistic regression. You know that, right? Okay, what do we mean by counts? Look at what happened now. I gave you an example the other time about how some politician allege that there was electoral malpractices in the last election. Now, do you know that if they carry out investigation, probably you go from all the counties in the United States. If I go to county 1, okay, there's possibility that if I go to county 1, I think they needed to answer one question, and the response to the question is dichotomous. It's either there is electoral malpractices or not, right? Now, I will now, if this county say yes, there is electoral malpractices, I'm going to count that county as number 1. Then I will go to another county, investigate. If they say there is, that will be number 2. It means from binomial situation, we derive the counting. Because what are you counting? You're counting the number. How many, okay, in this county, do they have electoral malpractice? If they say no, that is 0. You're not going to count them. Okay, so what I'm trying to tell you now, when the n is large and the probability of getting the characteristics of interest is very, very small, then the MP will actually be equal to lambda. Okay, so we move from binomial distribution to Poisson distribution because the lambda that you have is actually the incidence rate. Okay, I'm going to give you an example now from medicine, cancer in a large population. Okay, now in a particular large city in 1919, they recorded 30 cases. Okay, if I want to find the probability now of that story, S equal to 30, all I'm going to do is to plug in 30 into that, depending on the number of lambda that we have. So if we know the yearly average number of cases, then we can determine the probability that we're actually going to have 30 cases of that. For instance, you can actually use this to determine, if you know the incidence rate of the Omicron variant of COVID, then what is the probability that, in the United States, we have 30 cases, then this distribution can actually be used to figure that out. But you know what? That is not where we're going. Now, take a look at this. I told you the other time, Poisson regression model can be used to model count data, and it can also be used to model contingency table. Now, take a look at this, a contingency table. If you take a look at this table now, okay, this table can actually also be modeled using the analysis of categorical variable. If you want to go by what we did last time, okay, what I'm gonna do today, I'm gonna walk you through the method we used before. And what we're going to do in part 2, which is going to be on Monday, we're going to use Poisson regression to model this as well. Because Poisson regression model can also be used to model analysis of categorical variable. Now, take a look at this. There was a survey conducted by General Social Survey in 1991, where they actually asked men and women whether they have belief in afterlife. Okay, they ask men and women whether they have belief in afterlife. And of course, when you take a look at this is the responses, I think 582 men were investigated, and 435 said yes, there is afterlife. And the 147 said no, or they are undecided. For female, 509, okay, female were investigated, and 375 believe there's afterlife, and 134 believe there's no afterlife. You get what I mean, right? Now, what is the essence of this research? We actually want to investigate whether gender play a role in the response. I'm going to say that again. We want to see whether men and women have the same perception, okay, of the belief in afterlife. That's exactly what we want to investigate. Okay, so we want to investigate this now. Okay, that is a question. Look at the question. I said, is belief in the afterlife independent of gender? Okay, so the null hypothesis is going to be there is no relationship between gender and the belief in afterlife, but the alternative hypothesis is going to say there is a relationship. Okay, and of course, if you want to model this using what we've done before, you're going to use chi-square, right? That's what you're going to do. Now, I think I showed you the other time. I think I presented on Wednesday how you can use how, right? Okay. Now, we've done that, and at the end of the day, you can see you remember all this, right? At the end of the day, we have a result. Now, take a look at the p-value. The p-value of the test is 0.6774593. The p-value is greater than 0.05, which means we are rejecting the null hypothesis. What is the which means we fail to reject the non-hypothesis, because it's greater than 0.05. So failure to reject the non-hypothesis actually means gender is independent of the response. It means there's no relationship. It means the perception of men and women, okay, are more or less the same. That is what it means. Okay, so because the p-value here is 0.67745993, it's actually greater than a 0.05 level of significance, and we're going to fail to reject the non-hypothesis because the non-hypothesis is going to tell you, okay, there is no association between gender and their belief on afterlife. And the alternative hypothesis is going to say there is a relationship. But right now, we are saying there is no relationship because the p-value is greater than 0.05. Now, what have we done here? We have actually used chi-square test. Okay. Now, and I want to, introduce you to how we can use Poisson regression model for the same data set. Why are we using Poisson regression model? Because when you take a look at the data set, this account is a count data. Look at that. It's a count. 435, 147. That's a count. And that is why Poisson regression can be used. Now, I'm going to walk you now through the Poisson regression. Now, introduce you to Poisson regression. Now, take a look at that. Poisson regression is defined as that. Model is Yij. Okay, follow Poisson with a parameter lambda Ij. The lambda Ij that you see, it means for each cell, you're actually going to have lambda. Look, what do I mean by cell? Look at that. Here, for 435, that's 147, 375, for 134, each cell, we have a lambda. Okay, so I'm going to show you that now. Okay, now the model is Yij, follow that. Now the Poisson regression model, I want you to see something now. Poisson regression model, officially, it is lambda Ij equal to lambda, okay, multiplied by alpha male gamma response. Why do I say alpha male gamma response? Because in this particular question, we are looking at the effect of gender on the response. And that is why the Poisson regression model is lambda Ij equal to lambda. You know, there are two forms of lambda, right? The other lambda is what we call, it's a baseline. We call it a baseline rate. Okay, and the lambda Ij is the Poisson rate for each cell. Okay, then you have alpha male and gamma response. Why do I say alpha male? Because I actually want to code. We got two levels of gender, right? We're coding male as 1 and coding female as 0. That is why we put alpha male. You can decide to also put alpha female. There's no problem. Or you put alpha gender. Okay. Now, if you look at the model here, that is multiplicative in nature. You can see that lambda multiplied by alpha male multiplied by that. Oh my God, in statistics, a multiplicative model will be very difficult to estimate. I want to say that again. A multiplicative model will be very, very difficult to undertake. Because of that, you know what we're going to do? We're going to transform the model. And how do we transform a multiplicative model? We introduce log. You remember when you were in the high school? When you're doing the log of this, log of that, you're thinking, oh, why am I doing this? This is the application now. Now, what is the log of a product? If I have A multiplied by B, what is the log of that? It's going to be log A plus log B, right? Because we want to introduce linearity into the multiplicative Poisson regression model. And that was why we log both sides. Oh my God, when you log lambda Ij, you have log of lambda Ij, log of that, and log of that. What does it become now? It's additive now. Because it is when the model is additive in nature, we can easily estimate parameters in the model. I'm going to say that again. When model is additive in nature, parameter can be easily estimated. But when model is multiplicative, it will be very complex. It's going to be cumbersome. It won't be easy at all to estimate parameter. Now, what does it look like now? That was why I said it's looking like a linear model now after taking the log transform. Okay. Now, at the end of the day, we're going to say log lambda is beta naught. Look at that. Then the log of alpha male, we're going to have beta 1 high male, beta 2. Look at that. What do we now have now? It's looking like a linear model. Then we can estimate parameters in it. Why do I have I, male, I, response? I is an indicator. We're trying to tell the world, okay, the predictor is categorical. And not only that, the response is also categorical. That is why we put high. Look at that. Okay. Now, I want you to pay attention to this now. How do we interpret? For instance, what we're dealing with right now, this is a Poisson regression model. We're fitting that. We're trying to look at the effects of gender on the response. Okay. Then what is the response? Believing after life, right? Now, if my beta naught, my beta 1, and my beta 2, how am I going to interpret it when I run the model? Take a look at that. You can see that I said log lambda is beta naught, right? Log alpha male is beta 1 high male, okay, and beta 2 high response for the other one. Okay, how are we going to interpret it? Please, I want you to see how it's going to be interpreted. The outcome is what we call the log of the expected cell count. In Poisson regression, the outcome that we call the response, it is called the log of the expected cell count. You know that in logistic regression, we call the estimate log odd estimate, right? But here, in Poisson regression, we call it the log of the expected cell count. How do we now interpret beta naught in Poisson regression? Beta naught is an intercept, right? What do we mean by intercept? In mathematics, the values of the rest of y when s equal to 0, right? Now, take a look at this. The baseline beta naught is the log expected cell count for female responding no. Why do we say female? Because we coded female as 0. A female responding no is like no. It's like no here is 0, female is 0 because we coded female as 0, and no response is 0. Therefore, the beta naught represent the expected, the log expected cell count for female responding no. Then how do we interpret beta 1? Okay, the beta 1 is the increase in log expected cell count for male compared to females. And that was why I take a look at the model. What do you see in the model? We coded male as 1. When we coded male as 1, it means we're going to be comparing male with who? With female. And that was why the beta 1 there is basically going to be the log, the increase in the log expected cell for male compared to female. Then what about beta 2? Don't forget the beta 2 has to do with response, right? Now, which response do we code yes? With 1, we do coded 1 is yes. So the beta 2 is going to be the increase in log expected cell count for response yes compared to no. Now, you know what we're going to do next? What we're going to do next on Monday is I'm going to walk you through the code in how to fit Poisson regression model to this. That is what we're going to do on Monday. Now, before I go today, I have an announcement. I I was supposed to travel to Africa for what is it called? For a conference where I want to present and invite me to present something that has to do with everything that you have been doing. Okay. And because of the COVID stuff, I'm not going to go, and I want to do that through the Zoom. Now, I want to tell you on Tuesday by 8 a.m. Central Time, if you are interested in joining the Zoom to listen to my presentation, the presentation will center on everything that we have been doing from day one, because I actually want to discuss what we call the analysis of contrast in mixed models. And in that very day, I'm going to touch linear regression, logistic regression, Poisson regression. In fact, I will cover a lot of models in statistics that some of you may want to listen to. So I'm going to share the link on the announcement section for those of you that may want to attend. It's December 7th, 8 a.m. That is going to be on Tuesday. Okay. I think this is all what I have for you today on Monday, what I'm going to do. If you look at what I'm doing now, if I now want to run the Poisson regression in R, let me quickly say this before I go. If I want to run that in R, I will write out the count, the observed value. Okay. Now, I will be anywhere you see 1 under male, that is for male. Anywhere you see 0, that is for female. And under yes, anywhere you see 1, that is yes response. Anywhere you see 0, that's a no response. So this is how the data layout is going to be when I want to run it in R. So I'm going to continue from here on Monday, and you'll be able to see whether we're going to have the same decision using the chi-square test in the analysis of categorical variable and the Poisson regression. Okay, make sure you stay safe and have a lovely weekend.
I have a quick question on the Zoom.
Okay, go ahead.
So I think you said about our second test, the midterm, that we could get half credit on some of those multiple choice questions, but mine didn't show up on Canvas.
I've already graded that. Okay, you know what you can do? If your own did not show up, please send a message to me, and I'm actually going to grade that right away.
Okay.
So if you write a multiple choice in a multiple choice in exam, for those of you who wrote exam online, and there are some questions that have to correct answers. If you get one right and you were marked wrong, because if you get one right and you were marked wrong, it means you are losing 4 points. Please reach out to me. Automatically, I will regrade that. Have I answered your question?
Should I just email the email given to us in the syllabus?
Yeah, just email to the email that you see in the syllabus. My email is working fine now, and I'm gonna attend to that. You get me, right?
Thank you so much.
You're welcome. Okay.